Department of Economics, Berhampur University. So today we are going to discuss on consumer's equilibrium under indifference curve approach. So there are two things here. One is consumer's equilibrium and the other one is indifference curve approach. So first let's move to consumer's equilibrium. So when we start in microeconomics, normally we start with consumer's equilibrium. What is consumer's equilibrium? For how consumer maximizes its level of satisfaction or utility. So the concept of utility, what is utility? Utility is the want satisfying capacity of a commodity or service. Okay. So when a consumer goes to market, consumer has different alternatives at its disposal to choose. So which alternative the consumer is going to choose and which alternative is giving the consumer the maximum level of satisfaction, that is the subject matter that we are going to discuss here. How the consumer can maximize its level of satisfaction or utility. So the concept of utility, it is a function of different commodities that the consumer consumes or the different commodities in the consumer's basket. Okay, so this is how we can write it. U is a function of Q1, Q2. Suppose there are n number of commodities. So U is a function of the consumption of amount of commodity Q1, Q2, Q3 up to Qn. And one thing that is to remember here is that utility is additive. Utility is additive. That means utility depends upon the amount of consumption of a commodity that the consumer is consuming, right? And utility, utility function, the basic assumption for utility function is it is a single valued continuous function. Single valued continuous function. Also it satisfies it is a regular strictly quasi-concave utility function. So let's start. Suppose for ease of understanding, let's take utility as a function of Q1 and Q2, right? So if suppose there is no constraint for the consumer to consume these two commodities Q1 and Q2, then there is no problem for the consumer. It can go on consuming the amount or the commodity up to its level of satisfaction is maximum. But suppose there is a constraint for the consumer, right? Suppose there is a constraint might be in terms of, like, suppose the budget is a limit or constraint for the consumer. So suppose the consumer has Y level of income that it has to spend on the two commodities. So the budget or the income constraint will be Y is equal to P1 Q1 plus P2 Q2, right? Suppose the whole of the amount of Y or income the consumer has to spend on Q1 and Q2, given the prices of P1 and P2, given the prices of Q1 and Q2 as P1 and P2, which are given for a time period, for a given time period, or this is what we are discussing, it is for a static analysis. So we are discussing it for a time period. We are not taking it to dynamic analysis. This is a static analysis. So for the static analysis, our problem is to maximize, the consumer wants to maximize its level of utility, which is a function of Q1 and Q2, two commodities, given subject to the income constraint, that is with the consumer, which is the equation for the budget line or income constraint is P1 Q1 plus P2 Q2. Y is equal to P1 Q1 plus P2 Q2. So this is the problem, that how to maximize utility given this budget constraint. So there can be two types of solution with this regard. One is graphical solution and the other one is mathematical solution. So what we can say, one is graphical solution and the other one is mathematical solution. Mathematically, how we can derive? So here we will focus more on mathematical derivation and briefly I will tell on graphical derivation of this consumer's equilibrium, right? So this is one part, consumer's equilibrium. Then coming to indifference curve approach, we talked about utility, right? Utility as a function of Q1, Q2 up to Qn if there are n number of cases, and for ease of understanding we have taken two cases, Q1 and Q2. So now the problem is how to measure it, how to measure utility, right? How to measure utility. So there are many schools of thought in this regard, starting from Marshall. So who will focus on indifference curve approach, which basically says that utility is measurable in ordinal terms. That means we can order the level of utility that we are getting from the consumption of the commodities, right? We can order them, and there are some basic assumptions upon which this analysis is based upon, like consumer is a rational human being. Of course, this is the first assumption that we normally make in economics, that a consumer always wants more of something than less of it, right? And there are some other assumptions like transitivity, completeness, and your reflexivity. These are some of the assumptions upon which your indifference curve is based upon. I am not going to deep detail into that. So let's start with indifference curve. Yes, indifference curve approach. So what it says, indifference curve, this approach says that what is an indifference curve? Okay, first of all, what is an indifference curve? So indifference curve is a locus of the points of two combinations of two commodities that gives the same level of satisfaction to the consumer. So let's draw one indifference curve. So indifference curve, on the axis we take good X. Suppose there are two commodities, we have taken Q1 and Q2. So let's take it good Q1 and good Q2. So your indifference curve will take a normal convex shape like this, okay, where each of these points, each on the points of the points on the indifference curve, it shows the same level of satisfaction to the consumer. It gives the same level of satisfaction to the consumer. That means at point A, B, C, although they show different combinations of two commodities, like suppose this is Q prime, Q double prime, Q triple prime, and this is Q2, and Q1 prime, Q1 double prime, and Q1 triple prime. Suppose these are different combinations of Q1 and Q2 commodities, but they give the same level of satisfaction to the consumer. This is what this IC approach says. So there are other properties also, like as I move to the higher indifference curves, this gives higher level of satisfaction to the consumer, right? And then how to take this, if we'll take your budget line into consideration, then we have to draw the budget line here. All this indifference curve taken together, this is called indifference map. Then coming to budget line, let's suppose let me draw the budget line again in another graph. I am doing the same. Suppose this is the budget line, and this is Q1 and this is Q2, and this is the indifference curve map of the consumer. So this is IC1, IC2, IC3, IC4, as I told that higher indifference curves gives higher level of satisfaction to the consumer. Now this is the budget line of the consumer. Suppose this is BL. BL is the budget line of the consumer, and where the consumer attains highest level of satisfaction, so we have to match the budget line with the indifference curve of the consumer. We have to see where they both are equal, right? They both are equal, and which point is giving maximum satisfaction to the consumer out of those points. So there are 3 points, like suppose I am giving it A prime, B prime, and C prime. 3 points where the indifference curve is equal to the budget line. But see, A prime, B prime, and C prime. But what you can see, the indifference curve which is tangent to the budget line is the highest indifference curve that the consumer can move to, right? So this is the point of equilibrium where we can say that the consumer maximizes its level of satisfaction, right? So what is this point? How we can define this point? This point satisfies two conditions of equilibrium. First condition is the slope of the So there are two conditions that must be satisfied at the point of equilibrium. First one is the slope of the budget line should be equal to the slope of the budget line that I am writing here, BL, is equal to the slope of the indifference curve. The slope of the indifference curve, right? Slope of the indifference curve. The slope of the budget line, otherwise we know that this is, we can also derive it, that is equal to P1 by P2. Here P1 represents the price of commodity Q1 and P2 represents the price of commodity Q2, is equal to the slope of the indifference curve. What is the slope of the indifference curve? Suppose we are taking indifference curve, we have taken to that utility is a function of Q1 and Q2, right? And what we know that on an indifference curve, the level of satisfaction is same. That means change in utility is zero. Level of utility is same. That means what? Change in utility is zero. What we can write? du on an indifference curve, change in utility is zero. If we will take the total derivative of this with respect to of this, that will be zero on any indifference curve. So what it reflects, if we will write it, so it will be partial derivative of utility function with respect to Q1 into dQ1 plus partial derivative of U with respect to Q2 into dQ2 is equal to 0. This implies partial derivative of utility with respect to Q1 into dQ1 is equal to minus of partial derivative of utility with respect to Q2 dQ2. This implies minus of dQ2 divided by dQ1 is equal to, if I am replacing partial derivative of utility with respect to Q1 as F1. That means that is the marginal utility of Q1 commodity, and partial derivative of utility with respect to Q2, that I am replacing by F2. That is the marginal utility from commodity, from the consumption of commodity Q2. So now what I can write? It is minus dQ2 to dQ1 is equal to F1 by F2, right? This we can say, that means what is minus dQ to dQ1? That we can say that is the slope of the indifference curve. Slope of the indifference curve, it represents for a unit change in Q1 how much of Q2 the consumer has to sacrifice, right? How much change has to be made in Q2, commodity Q2, that is the slope of the indifference curve. So slope of the indifference curve, we can also represent it in terms of the ratio of the marginal utilities of the two commodities Q1 and Q2, that is minus dQ to dQ1 is equal to F1 by F2. So here I can write slope of budget line is equal to the slope of the indifference curve, or that is equal to F1 by F2 is equal to what? Otherwise we can say it marginal rate of substitution of Q1 for Q2. Marginal rate of substitution of Q1 for Q2, that we can write, right? So this, and the second condition is what? The indifference curve is convex to the origin at the point of equilibrium, right? The indifference curve, the IC is convex to origin at the point of equilibrium, the indifference curve is convex to origin at the point of equilibrium. Right, so these are the two conditions. The first one is the necessary condition. The slope of the budget line is equal to the slope of the indifference curve, and the second one is the sufficient condition, that is the indifference curve has to be convex at the point of equilibrium. At the point of equilibrium is the second order sufficient condition. So now with this graphical brief introduction to the graphical solution of consumer's equilibrium, let's move to the mathematical solution or mathematical derivation of this consumer's equilibrium. So now let's move to the mathematical derivation of consumer's equilibrium under indifference curve approach. So for mathematical derivation, as before we have taken already that utility, for ease of understanding that we are taking. Utility is a function of Q1 and Q2, right? I am writing utility as a function of Q1 and Q2, right? So our problem is to maximize this utility function. Maximize, I am again writing it, maximize utility, which is a function of Q1 and Q2, subject to the budget constraint, which we have taken Y as the income, is equal to P1 Q1 plus P2 Q2, where P1 and P2 are where P1 and P2 are the prices of Q1 and Q2, and respectively, and these prices are constant for a given period of time under analysis, because since we are talking about a static period analysis. So this we have to maximize, utility we have to maximize given the constraint. So how to do this? For this we have to make the composite objective function. Before, suppose you do not have any constraint, then there is no problem, you can go with simply your objective function. But when constraint is given to you, that becomes, you have to form the composite objective function taking your constraint into account, and that we will form taking the help of Lagrangian multiplier. So let's form that composite objective function, or otherwise we sometimes call it Lagrange function, as suppose that is, I am giving it the name Z. Z is equal to, so I am putting the objective function f of Q1 and Q2 plus lambda y minus P1 Q1 plus P2 Q2. Okay, so y minus P1 Q1 plus P2 Q2. Right, so this is the composite objective function or the Lagrange function, where we have added this constraint to the objective function through this Lagrange multiplier. What this Lagrange multiplier implies here? This is a positive constant. This Lagrange multiplier, it is a positive constant, undetermined positive constant. This is undetermined positive constant. Positive constant. This is undetermined positive constant, which reflects or which is the marginal utility of income. Marginal utility of income. What this reflects? This reflects 1 unit change in your income or in your budget, how it affects the utility of the consumer. For 1 unit change in your budget or income, how your utility changes, that is your marginal utility, which is captured by this lambda. right? So this is the composite objective function that you have to first form. Then after this, to know about the stationary points, if we move to the optimization, if you know the problems of optimization, when we optimize something, first we have to see what are the stationary points where the optimum points are optimum combinations are possible, right? So first we have to see the stationary points. And the stationary points, how we can get it from the first order partial derivatives of the function. So for maximization, the two conditions that we need are, first, for maximization, first condition for maximization, I am writing here the conditions of maximization. Maximization. So the first order condition for maximization are your, suppose this is z, we have taken the composite objective function as we have denoted it as z. So it will be dz is equal to 0. What does this implies? F1 is equal to F2, since we have taken only two commodities. So I am writing here F1 and F2 only I am taking. If you are taking n number of commodities, you can extend it to even n number of this marginal utilities. So this is equal to 0. So this is the first condition. F1, F2, what it implies here? Here F1 implies F1 is the partial derivative of the utility function with respect to Q1. That means change in utility due to 1 unit change in the consumption of commodity Q1. Likewise, what is F2? F2 is change in utility due to 1 unit change in the consumption of commodity Q2. Right. So your first order condition is F1 is equal to F2 is equal to 0. That you have to make. And this will give you the stationary points where the function might attain, the function may have different, like maximum point of maximum, point of minimum. It can have different points. Like suppose these are the points, suppose this is the function. So this is a point of maximum, this is another point of maximum, this is a point of minimum, and this is a point of minimum, and this is a maximum, and again this is a minimum. Sorry. So these are the stationary points, right? These are the stationary points, and the first order condition, it gives you those points, but you don't know whether these points are maximum or minimum. To know whether these points are maximum or minimum, you have to go for the second order condition. You have to know the second order condition. Second order condition means whether the function is suppose here, whether d square z, for maximization d square z, the second derivative, it should be less than 0, or this is the point. So d square z, it should be less than 0. It is falling after this point, reaching this point of maximum. So that is why d square z should be less than 0, right? So this is the second condition that should be satisfied. And if there are no constraints, in that case, you can simply take the Hessian determinant, and simply suppose for the second condition, Hessian determinant you can take, Hessian determinant, which is formed taking the second partial derivatives of the commodities. Like here we can take the first partial derivatives, we have denoted as F1 and F2. So second partial derivatives we can take F11, F12, F21, F22, right? So this is the Hessian determinant, and it should be less than 0 for your maximization. The condition it should be less than 0 for maximization. But if suppose there is a constraint, then you have to form the bordered Hessian determinant. So here the Hessian determinant, it becomes the bordered Hessian determinant, right? bordered Hessian determinant which is formed taking the constraints into account or the constraint at its borders. That is why the name bordered Hessian determinant. So let's move to find out these two conditions of equilibrium, right? Sorry. So first condition, first order condition, FOC I am writing it. So del Z to del Q1, right? Del Z to del Q1. So what is that here? It is del U to del Q1. First this I am representing as U here, and so Q1, since we are taking partial derivative, only this term is having Q1 with it. So we can directly write it minus lambda P1 is equal to 0. Okay. So this is del U to del Q1, that is otherwise your F1, we can also write it minus lambda P1 is equal to 0. Lambda, this, if we'll open this bracket, there will be three terms, right? One is lambda Y, other one is lambda P1 Q1, and the third one is lambda P2 Q2. And first one is lambda Y, where there is no Q1 term, so that will be 0. It is a constant. Since we are taking partial derivative, it will be 0. The second term, in the second term there is the Q1 term, that means pi minus pi P1 Q1. So that is why minus pi lambda P1 it remain, minus lambda P1 remain is equal to 0. So put it equation number 1. Then next is del Z to del Q1 is equal to del U to del Q2. This is for Q2 minus lambda P2 is equal to 0. Minus lambda P2 is equal to 0. So put it equation number 2, and the third equation that we have to do is del Z to del lambda itself is equal to Y minus P1 Q1 minus P2 Q2 is equal to 0. This is equation 3. Right. So these are the three equations from which we have to find out the stationary points. Right. So am I erasing it? So before erasing, let me denote the first equation as Z1, the second equation Z2, and the third equation as Z3. So from Z1, from this first equation, what we are getting is F1 minus lambda P1 is equal to 0. This implies F1 is equal to lambda P1, or lambda is equal to F1 by P1. This we are getting from equation 1. From equation 1, this we are getting, right? Likewise, from equation 2, we are getting lambda as lambda is equal to F2 by P2. From equation 2, what we are getting? We are denoting del U to del Q2 as F2. F2 minus lambda P2 is equal to 0. So F2 will be equal to lambda P2. So lambda is equal to F2 by P2. So from these two equations 1 and 2, what we are getting is F1 by P1 is equal to F2 by P2. F1 by P1 is equal to F2 by P2, or otherwise what we can write for this is equal to, so I am erasing now it. Sorry. So from this what we are getting is F1 by F2 is equal to P1 by P2. And if we go back to the graphical solution, we had also got the same solution or the first order condition for this. That is the f1 by f2, what we can say it, the slope of the indifference curve. Slope of the indifference curve is the ratio of the marginal utilities of the commodities, that is marginal utility of commodity 1 to marginal utility of commodity 2 is equal to the slope of the budget line, which is the price ratio of the two commodities, that is P1 by P2. Okay, so this is the first condition that we derived mathematically for the consumer's equilibrium. So that what does this implies? That this is the condition where you can get the stationary points, right? The points, the combinations of the commodities where the consumer can maximize. So whether this point is maximum or not, that we can verify, that we can get from the second order condition only. So the second order condition, for the second order condition, since it is a constraint optimization problem, we have to take the help of border Hessian determinant, right? So let's move to the border Hessian determinant. So the border Hessian determinant is formed taking the second partial derivatives into account, right? We have to form the border Hessian determinant taking the second partial derivatives into account. So the second condition or the sufficient condition, second order condition for mathematical derivation, for that we need all the three equations that we derived in the first order condition. So that is why I have already written these three equations here. So we have to take the help of these equations for the derivation of the bordered Hessian determinant. So let's start. So bordered Hessian determinant, I am writing it, denoting, normally it is denoted by H bar. So is equal to, let's take, suppose it is, first I am writing Z11, Z12, Z13, Z21, Z22, Z23, Z31, Z32, Z33. So this we have to derive from this. So here Z11 is equal to partial derivative of Z1 with respect to Q1. Z12 is equal to partial derivative of Z2 with respect to Q1, and Z13 is equal to partial derivative of Z3 with respect to Q1, and likewise all the other derivatives we have to define, right? So let's see first Z11. If we will do the partial derivative of Z1 with respect to Q1 again, so what we can find, in the first term only Q1 is there. Since this is the first partial derivative, for the second partial derivative with respect to same commodity Q1, I am writing here F11. This is the second partial derivative in commodity Q1, and since in the second term there is no Q1 term, so it will be 0. So first for Z11 we got F11. For Z12, then Z12 is the partial derivative of Z2. This equation, this equation with respect to Q. So it will be F12. Since here this F2, what is this F2? F2 is partial derivative of U with respect to Q2, right? So if we will derive it, we will partially derive the same with respect to Q1. We can write it F12. Here we cannot take it as a constant. See, F2 is, what is F2? F2 is partial derivative of U with respect to Q2, right? You can ask that since there is no Q1 term, so how we can write it F12? We can write it as F12 because utility, when we are considering utility, it is a function of Q1 and Q2 both. It is a function of Q1 and Q2. If we are writing U means Q2 term is there, Q1 Q1 and Q2 both terms are there. So we can partially derive this and we can write it as F12. So, and the third will be partial derivative of Z3 with respect to Q1. So, in the first term it is Y, no Q1 term. In the second term Q1 term is there. So, it will be minus P1. Partial derivative of minus P1 Q1 to Q1 will be minus P1 only. Right? And in the third there is no Q1 term, so it will be 0. This will be constant, it will be 0. Likewise, all the other derivatives we can find out, and with that we can write it as F21, F22 minus P2, and here it will come. The third will be Z31. What is Z31? Z31 we can define it as partial derivative of Z1 with respect to lambda. So, if we will see partial derivative of this equation with respect to lambda, first term there is no lambda, second term there is the lambda term. So, here the partial derivative of this term with respect to lambda will be minus P1. So, minus P1, it will be minus P1. That is why I have written here minus P1. Likewise, the partial derivative of the second equation with respect to lambda will be minus P2. And the partial derivative of the third equation with respect to lambda will be 0 because no lambda term is here. So, it is 0. Now, our border Hessian determinant is formed here. Okay. And the second equation, second row, I have not defined it. Okay, well, again I am going to second row, Z21. Here Z21 is partial derivative of Z1 with respect to Q2. Likewise, Z22 is partial derivative of Z2 with respect to Q2. Likewise, Z23 is equal to partial derivative of Z3 with respect to Q2. Okay, with this we come to this border Hessian determinant, and this has to be greater than 0 for your secondary condition to be satisfied. That means for the convexity to ensure the convexity of the indifference curve, you need to have your border Hessian determinant greater than 0 for maximization, right? So I have written here the border Hessian determinant that has to be greater than 0 for the secondary condition to be satisfied. So let's simplify this determinant. So this is equal to, we can write it, is equal to F11 into, so we have to, if we have to solve this determinant, I suppose that you have the prior knowledge of matrix and determinant how to find out. So F11 into F22 minus P2 into minus P2. Right. So this I am putting here. So F11 into, I have left 0 here, sorry, I have made a mistake here. So this we have to multiply 0 here. Let's multiply 0. F22 into 0. F22 into 0 minus P2 into minus P2. Okay. So then minus F12, again we have to take F12. So this we have to omit and this row we have to omit. So what left is F21 into 0, F21 into 0, F21 into 0 minus P2 into minus P1, minus P2 into minus P1. Okay. So F21 into 0 minus P2 minus P1 into minus P1, then plus minus P1 plus minus P1. Now I am omitting this column and this row. So what left is this one. So it is F21 into minus P2 minus F22 into minus P1. Okay, and this has to be greater than 0. You have to put here, this has to be greater than 0. Okay, so is equal to, now let's simplify it. So I have left some brackets. Okay, right now. So first one, let's simplify the first one, F11. So this will be 0, F22 into 0, it will be 0. And then minus into minus P2 into minus P2, so it will be minus P2 square. So we can write here F11 into minus P2 square, right? Minus P2 square. So then minus, here minus is there. So first term, again it will be 0, F21 into 0, it will be 0. And in the second term, it will be minus P1, P2. 3 minus symbols are there, so it will be minus P1, P2. So what remains is F12 into minus P1, P2, right? Minus P1, P2. F12 minus P1, P2. Then the third term, is here minus P1 is there. So let's first see what is there in the bracket. So within bracket, what will it will be F minus F21 P2, right? F minus F21 P2, and this will be plus F22 P1. And if we multiply the P1 with these two terms, it will be, finally I am writing the final terms here. So it will be plus F21 P1 P2, right? It will be F21 P1 P2, and then the second term will be minus F22 P1 square. F22 P1 square. So now again I am writing here. It is minus F11 P2 square. F11 P2 square. This is plus F12 P1 P2. Then F21 P1 P2 minus F22 P1 square. I have left greater than 0 here, so you put it greater than 0 here, right? F22 P1 square, it is greater than 0, right? Now what we know is F12 is equal to F21 through Young's rule, that is the cross partial derivatives are equal. So F12 we can write this as either F21 or F12, you can write whatever. So it is 2, we can write 2 F12 P1 P2. So how we can write it? So this is minus F11 P2 square plus 2 F12 P1 P2 minus F22 P1 square, that's greater than 0. Okay. So now, so this implies, please put implies symbols here. I have written simply equal to. So this implies that this we now will reach up to here, right? Okay. So from this, here also another thing we can make. Let's it will not cover now. Let me erase it and do it. Otherwise, I am writing it in this side. Okay. Now, what do you know that what is the relationship between from here? We have to put we have to represent this equation in terms of F1, F2 and P1, P2. Okay. So now let's substitute, and substituting F1 by F2. What we know that F1 by F2 is equal to P1 by P2, right? So we have to substitute this here in some terms, right? Suppose this implies, and from the last equation itself I am starting, minus F11 P2 square. So let me erase this portion. I am erasing this portion. I am just keeping the last two equations or last one equation. So for it will be easier for derivation. So let's write it here. Let me write it here again. This implies, I am taking the first one as it is, F11 P2 square plus 2F12 P1. In place of P1 I am putting the, what I am putting, so P1 we can here derive from this relationship. P1 is equal to F1 by F2 into P2, right? So this and this relationship, from this relationship I am putting here P1. In place of P1 what I am writing, F1 by F2 into P2, right? And another P2 is there. P2 is already there. One P2 is there, and I have just substitute P in place of P1, F1 by F2, P2, right? Minus F22. In place of P1 again, I will put the same F1 by F2 into P2. Okay, since square term is there, so all these terms will be in square terms. So it will be F1 square by F2 square into P2 square. It should be greater than 0. What is there in the equation. So now from this what we can do is we can take minus P2 as common from all these three terms. P2 square minus P2 square, we can minus P2 square, we can take common for all these three terms, right? So now what remained is F11 plus 2F12 F1 by F2 minus F22 F1 square by F2 square. It has to be greater than 0, right? Now so this has to be greater than 0. So now what we can write, I am erasing the last one, last equation here. So what we can write here is simply we can write F11 plus 2 F12 F1 by F2 minus F22 into F1 square by F2 square is greater than 0. So now we came to here. Now taking the greatest common factor into account, F2 square. So now it will be F2 square will take the sum of all this. It will be F11 F2 square plus 2 F12 F1 F2 minus F22 F1 square. This has to be greater than 0. What this implies? That this implies F11 F2 square plus 2 F1 2 F1 F2 minus F22 F1 square, it should be greater than 0, right? So I have just taken this to this side, so it will be greater than 0. So now I am erasing this upper portions. So what we can write here, this you can write as minus of f22 f1 square minus of, somewhere I made a mistake. Okay, let me erase it. Now in this equation, by replacing f1 by f2 is equal to p1 by p2, we are getting this implies minus f11 p2 square plus 2f12. In place of p1, I am writing f1 by f2 into p2 from this relation into p2 is there, so p2 minus f22. In place of p1 square, I am writing f1 by f2 into p2 its whole square. So it is f1 square f2 square into p2 square, and it has to be greater than 0, this term, all these terms. So from this, what we are getting is, we can take p2 square as common from all these three terms. So let's take it p2 square, and within bracket we have minus f11 plus 2f12 f1 by f2 minus f22 into f1 square by f2 square. All these terms, it has to be greater than 0. So now there are two terms, one is a square term and the other one is a bracketed term. Since this is a square and the multiplication of this with the bracketed term is greater than 0, that means it has to be positive. The bracketed term, what we can conclude, that the bracketed term has to be positive. So now what we can write, let's take the sum of the bracketed term directly. So let's take the sum. So it is f2 square I am taking. So it is f11 f2 square plus 2f12 f1 f2 minus f22 f1 square is, it should be greater than 0. Now let me erase the past this equation. This implies, what this implies is, now what we can write, minus f11 f2 square plus 2f12 f1 f2 minus f22 f1 square is greater than 0. Now just to take this minus as common, so what we have is f11 f2 square minus 2f12 f1 f2 plus f22 f1 square. It has to be, so it has to be positive. So what this implies, minus and this bracketed term, the multiplication of this should be greater than 0. That means this bracketed term has to be negative to make the whole term positive, right? That means what we can conclude from this? This implies f11 f2 square minus 2f1 f12 f1 f2 plus f22 f1 square, it has to be greater than 0, which is the condition for your, sorry, this should be less than 0. Sorry, this has to be, the bracketed term has to be less than 0. So, and this is the condition for your convexity of the indifference curve. If we go through the convexity of indifference curve, this is the condition that must be satisfied to ensure that the indifference curve is convex to origin or convex downward. Okay, so this condition has to be satisfied to attain consumer's equilibrium, and this is the second order condition for consumer's equilibrium. So thank you. This is all about the mathematical derivation of consumer's equilibrium through indifference curve approach. Thank you.